Hello, this is FRQ Practice Set 7, Question 3. So a uniform rod is 2 meters long, has a mass of 4 kilograms. At rest at an angle of 60 degrees above the horizontal, is pivoted around about a horizontal frictionless pin about one end as shown right. So part A, calculate the initial energy of the system. So the rod is released from rest. So which means it starts at rest, which means the only type of energy there is potential energy. So how do you find that? Part A, E initial equals potential energy equals mass times gravity times height. So mass is 4 kilograms, G is 9.8, and height. So we take the height from the center of mass, and the center of mass of a rod is right in the middle. So this is the height. Well, how do you find that? Well, what you can do is, this hypotenuse is L over 2. And you can take L over 2, sine of 60 degrees to find this height. So L over 2 sine 60. So 4 times 9.8 would be 39.2. And L is 2, so 2 over 2 equals 1. 1 sine 60. So 39.2 sine 60 equals 33.95 joules. That is our E initial energy. Part B. What is the angular acceleration of the rod at the instant it is released? So to find angular acceleration, we can use Newton's second law with torque. Net torque equals moment of inertia of the rod times alpha. So net torque equals net force times moment of arm. The moment of inertia of a rod is 1/3 times mass times the length of the rod squared, and then alpha. So the only thing, when the rod is released, it falls down, which means the force acting upon it is force of gravity and the moment of arm. So force of gravity affects right in the center. So moment of arm is the perpendicular distance between the line of force. So here's FG, and the line of force is right here. Perpendicular distance between the line of force and the moment of the axis of rotation. So the axis of rotation is right here, and you draw a straight line here, axis of rotation and line of force, a perpendicular line that creates a perpendicular angle right here, and this will be our moment of arm. Distance between the line of force and the axis of rotation. And what is this? This is L over 2 cosine of 60. Because this is the entire triangle. Hypotenuse is L over 2, and cosine of 60 is right there. So L over 2 cosine of 60 equals 1/3, mass is 4, L equals 2, alpha. And L equals 2, so I'll just erase this and make this 1. So F of G is mass times gravity, which is 4G, minus, or times cosine of 60 equals, this whole thing will be 16 over 3 alpha. And 4 times G is 39.2 times cosine 60 is 19.6 equals 16 over 3 alpha. And you isolate for alpha, and you get alpha equals 3.675 radians per second squared. That's part B. Part C. Once the rod is released, and as it rotates, does its net torque stay constant, increase, or decrease? Alright, so net force, or net torque, is dependent on or inertia. Net torque is equal to, as we saw here, Fg, net force is only Fg times moment of arm, which is L over 2 cosine theta. So net torque is dependent on theta. And as the rod falls down, the theta becomes smaller and smaller. And which means cosine of that getting smaller theta increases. And as a result, net torque increases as the rod rotates downwards. Part D. Rank the following from greatest to smallest. Angular acceleration of point A, point B, and point C. So point A, point B, point C. So alpha A will equal alpha B equals alpha C. Why? Because all of the points will move at the same theta at the same time. So imagine this is the rod and this is the ground. It will reach 60 degrees every point for points A, B, and C at the same time. Which means not only does it have the same angular velocity, omega, it also has the same angular velocity, angular acceleration. So part E, it asks determine the greatest to smallest angular velocity. As you said before, since all the points reach the same, move the same amount of theta at the same time, it has the same omega and the same angular acceleration, alpha. Part F. Write the following from greatest to least. A tangent, A, B, and C. Okay, so A equals alpha times R. So alpha, as we saw, is always equal, but the R changes depending on the point. So A has the smallest R, B has the second smallest, and C has the largest, which means C is the greatest in acceleration tangent. Like that. This should be a smaller A. Okay, part G. Rank the following from greatest to smallest. This is the last one. A centripetal of A, B, and C. So, A centripetal equals V squared over R. And V squared, side note, equals R times omega. And you distribute the squared and you get R squared omega squared G. Omega squared over R. We can cancel here and here, and we get R omega squared. So omega, as we said in part E, will stay the same, so that doesn't matter. But R changes depending on where the point is on the rod. And as we said, point C has the greatest, so AC of C is greater than AC of B is greater than AC of A, because it has the larger radius and therefore the larger A centripetal. Okay. Turn this around. Part H. Calculate the time it takes for the rod's position to be perfectly horizontal. So, what I'm going to use is delta theta equals omega initial times time plus 1/2 alpha times squared. So we're going from 60 degrees to 0 degrees. So that's a change in 6 degrees. And 6 degrees converted to radians is the same thing as pi over 3. It starts at rest, so this will be 0 equals 1/2 alpha t squared. Now, what is alpha? Alpha changes depending on where the rod is, because it is dependent on cosine theta. Torque changes based on cosine theta, so alpha also changes based on cosine theta. So what we have to do is find the average acceleration to use across the entire problem. So first we'll derive for alpha, angular acceleration, torque equals I alpha, net force times moment of arm equals 1/3 ml squared alpha. Only force affecting torque is Fg. So it's just okay. Fg equals mg. R is L over 2 cosine theta. We can cross out this L and this L squared, cross out this M and this M, and we get G cosine over 2 equals L alpha over 3. And L equals 2 meters. That looks kind of like a 2. And then we divide both sides by 2/3 and we get 3G cosine over 4 equals alpha, which can be simplified to 7.35 cosine theta equals alpha. So to find the average acceleration, we need to use, so A average equals the integral of alpha. We're going to go from 0 degrees to 6 degrees. We're using degree mode, so we use 0 to 60. If you're on radian mode, you use 0 to pi over 3. This will be based on with respect to theta and over 60. And alpha would be equal to 7.35 cosine theta. We just plug it right in there. And in the end, multiply all that and divide by 60, and you get 6.07 radians per second squared. This is our alpha average. And we will plug that right into there. So pi over 3 equals 1/2 6.07 t squared. This will become 3.035 t squared. Divide both sides by that, we get 0.345 equals t squared. And t will equal 0.59 seconds. Oof. Okay, part I. Part I says, calculate the amount of time it takes the rod to travel the second half of its total angular displacement from 30 degrees right here to 0. So what we have is, we already have the time total, 0.59, and to find the second half, we can expand the total time into t1, the first half, plus t2, the second half. So we need to find t2, and that will equal t total minus t1. So in order to find t2, we had to find t1, or at least that's the easiest way. So to find t1, we'll also use the position function. This time it is traveling only 1/2 of 60 degrees or 30 degrees, and 1/2 of pi over 3 is pi over 6. Once again, it starts at rest, so this will be crossed out, since omega initial is 0, plus 1/2 angular acceleration is 6.07 t squared, 3.035 equals pi over 6 t squared. Okay. This will become 0.173 once you divide both sides by this. And we're left with t1 equals 0.42 seconds. We just plug that right here and plug t total into there. So we have t2 equals 0.59 minus 0.42, and t2 will equal 0.17 seconds. The second half will take 0.17 seconds to go through. Lastly, part J. Part J says calculate the total change in angular momentum of the rod about the pivot from 60 degrees to 0 degrees. Change in angular momentum. Angular momentum is change in L equals LF minus LI. And because it starts at rest, there's no angular momentum for the initial because there's no angular velocity because it's at rest. So change in L equals LF, which is equal to 1, which moment of inertia rod times omega F. But what is omega F? We can find that out by using the average. Something happened. I don't know whether or not it cut out some of the recordings, but here you go. I'll repeat again. Change in angular momentum equals LF minus LI. LI is crossed out because there is no angular momentum initial because it's at rest. Therefore, there's no initial angular velocity. So we're left with this. And I was about to do angular acceleration to find omega F. So crossed out. T. So omega F equals alpha times time, which is equal to 6.07 times total time, which is 0.59. And we're left with 3.58 rads per second. We'll just plug that right here. Equals 1/3 ml squared. M is 4, L squared is 2 squared, and then omega F is 3.58. Okay, you have all that. You can multiply that together to get 19.09 kilometers times meters squared per second. And that is it. Hopefully my low battery did not affect the video too much, but anyway, I'll see you in the next question.